Good morning, everyone. Welcome back to our seminar series. Today we have an external speaker, Konstanze Zwintz. She is a visitor here for a week. Actually, it's her last day today, I think, at IvS. She's been around this whole week, and several of you got the chance to talk to her already. So Konstanze comes originally from Vienna, where she did her master and PhD studies, I believe, and she also spent some time here in Leuven as a senior postdoctoral researcher, originally coming on Marie Curie Fellowship, I believe. That was, like
2012 to 2015.
2012, some time ago. But presently, Konstanze is a professor at the Innsbruck University in Austria, and she specializes on pre-main sequence stars, so early stages of stellar evolution, where she uses asteroseismology as a tool to probe interior physics of those young stellar objects. But not only that, she's also interested in all the accretion processes happening in those stars. But I will not take more time introducing Konstanze, even though I could have spent maybe an hour talking about her, but I will give the floor to you at this point, Konstanze, to you. Go ahead.
Thank you very much, Andrew. It's a pleasure to be back again after a long time. And as Andrew already said, I'm working on pre-main sequence stars with pulsations. And this work started with my PhD, and it has captured my attention. And I'm still feeling very passionate about it. And I think we're now in an excellent time where exciting things are happening. And I'm trying to share my enthusiasm with you now during the next minutes. So if we talk about early stellar evolution, maybe you all have some kind of a concept in your head how stars are formed and pass through their first stages. And you might ask yourself, why the hell should I care about what happens at the beginning? So I'm trying to convince you now. You might remember stars are born, Stars are born from giant molecular clouds, like you can see here. And depending on the properties that they get when they are formed, their further evolution is decided. Basically, their future fate is decided based on what happens at the beginning. And so if a star doesn't get a lot of mass, only very little mass at the beginning, then it will be a brown dwarf, and it will spend a very long, probably relatively boring life, billions of years, and not a lot will happen. So in the general picture that we have, if the star gets a little more mass, it turns out like something like our sun. A solar-like star, or star like our sun, will take billions of years burning hydrogen in its core. And then when the hydrogen is exhausted, it will go into the later evolutionary stages, becoming a red giant, planetary nebula, white dwarf, and then maybe the circle of life in stars closes, and the end product might then again have some influence on triggering star formation again. But if stars, I'm not used to this, I'm sorry, this is not mine. So if a star gets more mass than our sun, the more massive stars, they proceed faster. I think we all should know that about stellar evolution. So within millions of years, massive stars have exhausted the hydrogen in their core, and they move on in their evolution to red supergiants, supernovae, neutron stars, black holes, and then supernova explosion can again trigger star formation. So it really depends what these young stars, what properties they get, in particular what mass they get at the beginning. So still, why should we care? So let's stick to a star that we all know very well. We have the sun. We can study the sun, its activity, its spots, its pulsations, its flares, its surface, in everything. But we see the sun as it is today. The big question is, how did it get there? How did it become the star that it is now? So how was the sun as a young star? How was it formed? Why does it have this particular properties, including the planetary system? That is also connected, of course. And of course, this continues with the question, what will the future of our sun be? So this is a very relevant question and should demonstrate why we should care about understanding early stellar evolution better. So, of course, if you want to understand what happens at the beginning, you have to know the input physics if you want to do models or interpret observational data. So it's important to improve our understanding of the input physics of early stellar evolution. This can include topics like mass accretion, angular momentum transfer. Then what is the definition of a zero age? Just for a moment, think about, we always compare the life of a star with the life of human beings. A baby is born and you know exactly the date, the hour, the minute the baby is born. With stars, it's not that simple. They come from these molecular clouds that collapse. So when do you call the star a star? When do you set the age equals 0? This is not a trivial question, actually. Then how fast do these stars evolve through the primary sequence stages? What is their speed? And is the chemical composition changing, relevant? So what is the chemistry of these young stars? All these topics, example topics, illustrate that it's important to understand this input physics of early stellar evolution. And it's important not only to study stars, but it's connected to how planetary systems form, including comets and moons and smaller bodies. So the star formation is connected to planet formation. Of course, it tells us something about the history of our own galaxy, if we study star formation, and it of course happens also in other galaxies. Whatever we learn here can be compared to different studies in other galaxies. So I think with this I can convince you that this is one of the key topics in astrophysics that we should investigate. So if you think back again to your classes, you might have heard about a very traditional concept how primary sequence stars are formed. And I will show you in a moment how this is. So we know that, you've seen this picture, I'm using this again. So this is the molecular cloud where the stars are formed. And we know from observations with ALMA, for example, it's HL Tauri, a protostar is embedded in dust and gas. So that's how they look like, with the disk around and protoplanetary disks. So our traditional concept, and you will see now an animation, so I will explain before I started. The traditional concept following Hayashi and Henny, if you heard these names, assumes the young star at the beginning is a huge gas ball. It has, oops, sorry. I was like, okay, what happens? Is it me? Okay. These early stars are huge gas balls. For example, 55 solar radii for an initial model that will then end up with 2 solar masses. And of course, they assume the full mass is already there. And what you will see in the animation is a Hertzsprung-Russell diagram. You have luminosity and temperature. You will see, so now there is this big, huge gas ball in front. You have the evolutionary track that will be followed. You can follow this red point. It will tell you the stage the star is in. And if you look at how the structure of the star, this huge blob will get smaller, I promise. So everything that is hatched means it's convective. If the hatching is gone, it's radiative. So you will see how this concept assumes early stellar evolution. So we let the star contract along the Hayashi track. It's luminous and cold, so it contracts. It loses lots of luminosity, gains a little bit of temperature. You see how it becomes smaller. Then it's now on the Henny track, where it gains in temperature, and only little change in luminosities, until the hydrogen core burning starts. Unfortunately, this is a concept that is used in many fields outside of early stellar evolution modeling. And unfortunately, I have to say, this has not progressed. This is an outdated concept. So people who really work on young stars, they would never use this concept again. It has worked. It has the reasons why it worked, but this is an outdated concept. And why we can see that? We have observations, we have theoretical simulations that prove that stars at the beginning are not these huge gas balls. So there is a simulation from Matthew Bate, 2011, that shows you the time is running here on the top. And so it starts with a first core that has 2 solar radii, a mass of only a few Jupiter masses, and so we let the cloud collapse, and then we let a protostar form. Okay, that should have come later, but anyway, doesn't matter. So you see the simulation, the time is on top here, a few 10,000 years. So you see the density, the brighter it is, the denser the object. So you see a small first object form in these simulations, and you have a circumstellar disk, and in this disk, planets and smaller bodies can be formed. And now if you compare it to the picture that you've seen before, this makes a lot of sense. It looks very similar, actually. So this is why it's time to abort this old picture, in my opinion, and we should replace this by something more physical. So here you see again the classical evolutionary track coming from the top, and the accreting Freeman sequence track, the animation has started already, coming from the bottom right and slowly increasing. You see again the star that is radiative and convective, different zones, and how it gains mass through accretion. So this is a track where we start with a small stellar seed. We let it gain mass through accretion processes. In this case, it's a constant flow of matter. And we see a small kink when deuterium burning starts. And then here we have some kind of agreement, which is also good because it explains why the old concept worked so well. So this is so you have the sun as a comparison. We are here with the example of a 2 solar mass star. So if we take this constant accretion scenario and make a comparison to observations, what we see again here is in red are the classical tracks, so Hayashi and Henye tracks. And then in black you have what we call the accreting track. So that's it's a line that combines all different masses when accretion stops, and the star only contracts towards the thumb. So these are the black lines that evolve from this thick black line. And then for easy reference, you have the thumbs here, and you have lots of colored stars. These are Freeman sequence stars from different studies in the literature, of course, with observational error bars. So they are not plotted in this graph. There is one in the paper, of course, with error bars. And so what you should notice is that here there are some stars that are probably misidentified, so they might be in the Postman sequence stages, that are some with relatively large error bars underneath the thumbs, so very far beneath the thumbs. And there are a few stars that are above this accreting track. So theoretically, we would not see them. But the reason they are up here, there are several explanations, you can say. The observational errors were too large, and they are actually they should move down. But another explanation is that constant accretion is probably not a good physical description. Accretion will probably come in flows, which we call disk-mediated or episodic accretion. So there will be sometimes more matter coming towards the young star and sometimes less. And we'll see in a moment that leads to excursions in the evolutionary tracks. They get really crazy. And then even these stars could be explained. That's an option to explain them. So talking about episodic accretion. So that's the same we had before, just without animation. You still have the Hayashi track here and the Henye track, and we have our accreting Freeman sequence track with constant accretion. So we have a constant rate of mass that we dump onto the star. And then the turquoise line is now evolutionary track for 2 solar masses with disk-mediated accretion. So we let the accretion rate change with time. That comes from hydrodynamic models, these accretion rates, and they are just coupled to stellar models. And you can see what the star does. It does these luminosity excursions, and it has a relatively crazy behavior. It's not as smooth as as the other 2 tracks, but that can lead to a short moment where the star has a lot of more energy, a lot of more luminosity, and then it falls back to smaller luminosities. So, what is the difference? Just to illustrate, if we calculate early stellar evolution using the traditional concept with Hayashi and Henye, then this is a Kippenhahn diagram where you have stellar age on the x-axis. It runs from 10 to the 3 to 10 to the 9 for a 2 solar mass star in this example, and you have the enclosed mass. So the early stellar evolution starts with the full mass, And it starts with deuterium burning in the core. Everything is convective here. And then here is the start of the ZAMs, so start of hydrogen core burning. If I use disk-mediated accretion, then the Kippenhahn diagram, of course, looks different. We start with the small stellar seed, so there is not the full mass there yet. And the star gains mass through accretion. So first you see that how the star gains mass until it reaches its final ZAMS mass. You notice that there are, of course, a lot of regions that are convective, but there are also some radiative zones in the interior. And the most prominent probably thing to notice is the deuterium burning. When it's dark red, it means it's the burning region is the highest efficiency, basically, of the deuterium burning. So the deuterium burning starts off-center, doesn't start in the center of the star, but away from the center. The reason is that the matter falls onto the star, is redistributed, and in regions that are not in the core of the star, it gets hotter because of this distribution of matter inside. So the deuterium burning starts at a different age and at a different time, and it starts off-center. It's not core center burning. And you have different, so there is also a tiny little bit. Of course, this depends on the accretion history that is coupled to this. But yeah, on the ZAMs, they basically agree again, which is a relief that we did everything correctly. So I'm talking about these accretion rates. This was calculated as an example Kippenhahn diagram with one accretion rate. At the moment, we have 34 accretion rates, and I just give a small picture of them. They come out of these hydrodynamic simulations. And so what you basically see is every panel shows the age versus the accretion rate. And you can see sometimes they are more quiet, and sometimes they are not so quiet. And of course, then it has an influence how the star proceeds through the evolution. So what difference does it make if I use this another form to illustrate you the differences, what it makes? So the top panel is for the Freeman sequence, the bottom for the ZAMs. You see the fractional radius R over R sun, and you see the mass coordinate difference between the classical approach with Hayashi and Henye and the disk-mediated accretion approach. And it's in parts per thousand, so it's a small change in radius. The small change in the radius between these two models leads to a different interior structure. So on the Freeman sequence, I should also say this part is the convective part, is light gray. And then there is an overshooting region here in the Freeman sequence, and in the ZAMs, it's moved a bit outside. So good. What you have overplotted here and color-coded with salmon. So these black lines are accretion from these accretion histories. They are overplotted, and not all of them, because you would not see a lot, but the maximum and the minimum impact, basically. So you see that's basically the difference in mass coordinate versus fractional radius in the Freeman sequence and on the ZAMs. So it's only a few parts per thousand, and you would think, well, does this really have an impact? And I can tell you, yes, it does have an impact. And now we're coming to the connection with pulsations, because pulsations happen in the interior of stars, and they bring this information out to us. And so they feel this tiny radius difference. So my research goal is, my aim is, I would like to add to calibrate early stellar evolution. And I take young stars, and I search for oscillations of different types, and I do something that is now called Freeman sequence asteroseismology, so the study of pulsating young stars. So they're not, I heard not everybody knows about asteroseismology, so 2 quick slides on what pulsating stars are and how we record them. So many of you might know this. So if you cut a star in the middle, you can depict how oscillation waves travel through the star and bring information to the outside. It's also good to see this in an animation. So you have a blue and a red frequency that are very similar, but not quite exactly the same. And so they probe different layers in the star. In this case, it's P modes. We'll come to that in a moment. And you can see that the red goes a little deeper inside, the blue stops a little bit outside. And by investigating these differences, you can basically say something about this layer inside the star. So that's what happens inside. What happens outside is that the stars change their spherical symmetry. So they lose their spherical symmetry sometimes. So you have radial pulsations on the top, non-radial on the bottom. The simplest cases. So the pulsations distort the surface of the stars. And this lets us observe them. I am somehow not sensitive enough. Okay. So this lets us observe them. So this is a light curve, a recording of light over time. We observe them typically from space these days. This is the TESS satellite, and so we see these changes of the surface light. We collect them, and we can then deduce something what happens in the interior of the stars. Pulsations, everybody who had physics knows that you need two things for oscillations. You need a driving mechanism, and you need a restoring force. So what drives oscillations? A very broad mechanism is the heat engine mechanism that acts in many types of stars, in hydrogen, helium, metal ionization zones. And you can depict it like the Stirling motor. If you ever had that in thermodynamics, it's a heat engine, like the name says. It's also called opacity mechanism, because that's more the astrophysical term. Another driving mechanism, like the one the sun has, is stochastic excitation. Maybe it's the distance to the computer. Anyway, so the stochastic excitation is like a bell. If you ring a bell and you wait, a tone will fade out, and if you hit it again, you will have a tone again. That's stochastic excitation. You see a picture of convection in the sun. And the third, probably one of the main driving mechanisms, is you have close binaries and they force oscillations in each other. Then you have tidal effects that can cause oscillations. And then the restoring forces can be either pressure, then we call them acoustic or P modes. And these are actually sound waves. So the reason that you hear me, these are sound waves that travel through the air. Buoyancy is another restoring force, gravity or G modes, like the waves on a pond, gravity waves. And there are also Coriolis force is also a restoring force. These are Rossby or R modes. So at the moment for Riemann sequence oscillations, it's acoustic and gravity waves that we find. Okay, then you also might have seen this before in Hertzsprung-Russell diagram with all the different types of oscillators depicted. And so you see all these colorful patches, and you have, there is the TSAMs here, and you have the massive stars, and you have main sequence stars, and then after the main sequence, and you have the white dwarf cooling sequence, and then you ask yourself, so where are the young stars? And I'm always dreaming of making a three-dimensional diagram. I should really do that at some point, because the Riemann sequence pulsators are basically there. They have same mechanisms as the main sequence stars, but they are in a different evolutionary stage. So they are the ones that we know are about in this region of the Hertzsprung-Russell diagram. Okay, so but what is the challenge? You all have seen probably a light curve of a pulsating star. If not, this is a beautiful one. It's actually a young one. But they rarely look like this, or it's possible that they look like this, but you should not expect them to look as beautiful as this. Because young stars, as we have talked at the beginning about, they are still connected with their birth environment. So you can have irregular variability, like depicted here. They can show semi-regular variability that comes from the circumstellar disk and pulsations on top. So if you see the differences here, these are relatively huge irregular variabilities, and on top of that you have pulsations, and you have to figure out the pulsations in this variability. You can also have, of course, pulsations in binaries. This is actually RSK. a binary Freeman sequence pulsator. And you can also have spots on the surface, and then they have rotational modulation, and you have to somehow figure things out. Because it's not so easy to just take any star in the sky and say, okay, this is in the Freeman sequence stage. If you see something like this can help you actually, because this challenge that we have observationally is a potential. If I have a star with a disk and I get spectroscopy, then I will find emission lines, typically in the hydrogen lines. And then if I see emission lines, I know there is a disk, and that's already another very good indication that the star is young. I can use binarity to study tidally induced or tidally perturbed pulsations. So although a challenge per se, it can actually be a very interesting research topic. And if you have rotational modulation and pulsations, there's always an indication that there are magnetic fields. It's the question if we can detect the magnetic field, but it's an indication that the magnetic field is present. This means activity is happening. So the star is active. So every challenge in Freeman sequence star research can be a potential. So where are these stars? Let's zoom really into this field. So this is the theoretical instability strips for Freeman sequence stars. You have, again, a Kiel diagram. It's log G versus log effective temperature. You have the accreting track that we've seen before. And you have different regions. So red are G modes, blue are P modes, and the violet ones are the hybrid, where you have P and G modes. And we can populate this with some stars. You see that we have some SPB stars here. Here's the challenge. They are already burning hydrogen in their cores, so really Freeman sequence is really hard. We can just take at the youngest ones. Then we have the largest group, this A-type stars here. We'll talk about them in a moment. What we are currently missing actually is Freeman sequence gamma Dor stars, and I spoke this week already. There is a new candidate. I'm very enthusiastic about this. And there it turned out that there in M stars, there is an instability region. And we have one candidate that we found in test data in that region. What is missing here is, let me put it in this case, solar-like oscillations, because there is a different driving mechanism. And so we expect stars like our sun in about this mass range to show solar-like stochastic oscillations, P modes. They are predicted, but we have not detected them yet, and I'll come to that in a moment. But one step at a time, let's start with the group where we have more than 100, 120 stars known, Freeman sequence delta Scuti stars that are A and F type objects, masses between about 1.5 and 3 solar masses. And their periods are between 18 minutes and 6 hours. And these are these pressure modes. So restoring force is pressure. So I left out something because it's right old. I made one of my most important works here in Leuven, 2014. But I would more like to show you the impact of accretion. So we've spoken about this evolution histories with accretion. So in this graph, 8 accreting histories are shown, because if we would show all 35, you would not see a lot. So you see different luminosity excursions. Every accretion history of these 34 that we used gives a different path towards the SAMs. And it's probably also something that we cannot absolutely predict, because it's very likely a unique way how every star proceeds from its birth until it SAMs. So every star has a unique rate of accretion, and we can only try to find out what the difference are by using different models. But so these are 8 different ones, and they make crazy excursions. And so the question now is that I said a few minutes ago, we can use the pulsations to probe the interior structure that is different when we use accretion to model them. Here you see, again, the upper graph is the Freeman sequence, the lower is the SAMs. You see the frequency difference, again, between frequencies calculated based on models with accretion, this disk-mediated accretion, and minus the frequencies that come out using the classical approach. So you want to see if there is a difference and if we can measure this difference. That's the big question. Is it so tiny that we don't care, or is it as big that we have to care, and it is the latter. So what you see are violin plots. This is the radial order, so these frequencies are ordered by radial order. You see violin plots. If they are green, the models tell you that the frequencies are excited. If they are salmon colored, they are not excited. And every line, you might see there are some lines in it, is one of these 34 accretion models. And it's like the shape of the violin is a kernel density estimate, basically. So in principle, it tells you what is the difference between these two frequencies with different models. And then you have the dark gray area is the precision by 4 years observations by Kepler, and 1 year is the light gray. So if the best that test can deliver is 1 year observations. And you can see that the frequency difference on the Freeman sequence are so large that you should be able to see them with 1 year of test data. So this means it does have an influence how the star is formed, how we model early stellar evolution. And it carries out until the TSAMs. You can see still there are maybe some things that we would not be able to detect, but it's still also present on the TSAMs when hydrogen core burning has started. And this tells us that we cannot ignore what happens at the beginning, like it is done. Oops. Some strange things. Stars do not forget their past. This is something that many people assume. They start stellar evolution on a main sequence and forget what happens before. And I advocate that you should not do that, because you carry it with you in a further evolution. Another example that my PhD student just sent me yesterday out of his work, and I decided to include it, is another way to depict the same thing is you have the age in years between 10 to the 4 probably to 10 to the 8. And you have the scaled radius with a factor of 3.5, which is often used for solar-like stars as well. The solid lines are L equals 0 modes, and the dashed lines are L equal 1 modes. And then you have this thicker dashed line. This is the frequency of maximum power, so the highest amplitude, basically. And if you follow this with time, you see how it changes. This is the classical model. And I'm sure if you look at this, one of you can tell me what this kink is here. Any guess? Anybody has a guess? I'm sorry? No, that's earlier. It's probably somewhere here. But it's getting close. It's hydrogen core burning starts. That's where hydrogen core burning starts. This kink happens when hydrogen core burning starts. So this is the model as you use it probably with Hayashi and Henye. And if you use, this is one accretion history that is overplotted just for your information that you see how it is. If you use disk-mediated accretion, first of all, you notice the shape here and here of Numax is different. The overall shape of L equals 0 and L equal 1 is also different. The frequencies might be different. They are different. You notice the hydrogen core burning kink is looking different than here, and it starts earlier. So if you look here, you're about 10 to the 7 years, and this is before that. It just came out of his work yesterday. So it shows you that the frequencies feel the difference, and that you should not forget this. So towards the end of my talk, of course, there are several types of oscillators. These were now these P-mode 2 solar mass stars with delta Scuti type frequencies. You can go more massive and less massive, a reminder of the plot I've shown you before. So more massive are these young, slowly pulsating B stars, and we try to take the youngest ones. And gamma dwarfs, there are not so many, so This is something where every star counts at the moment. But this is a beautiful example that they exist. And although we don't have a lot of data for these stars, some have G-mode period spacings. So this is a young SPB star, actually. And one of my master students had the task to do a constant accretion. With higher mass, it's a little more challenging with accretion rates. Also, the simulations are not always provided to us because they are not so easy. So this is the mass range between 4 and 7.5 solar masses. So at the moment, for his master thesis, he focused on constant accretion. So, but similar to what we've seen before, this is again the accreting track. And here, from this accreting track, the evolution towards the sums happens. And if you ask yourself, so this is the birth line here from the old concept with Hayashi and Henry. The birth line was this concept where observations and theoretical calculations found an envelope, basically, that tells you stars above the birth line you should not be able to observe because they are still embedded. And so this is, for me, a good illustration why this concept worked for for a long time and reasonably well, because actually with accretion and the birth line, it has a similar location. So I think this explains why it worked quite well. So we are doing this now for SPB stars, and we have remodeled, or he has remodeled in his master thesis, 2 stars that we've formerly worked on with the classical models and tried to find the differences in mode identification. So the power of these G-mode pulsators is, as you might well know, that you can study the core to envelope rotation and the evolution of angular momentum, and then connect to the later stages to have a global picture about this. The next thing is lower masses than gamma dwarfs. We come, what I said, these solar-like stars. They should be late F to early K type, masses between about half a solar mass to 1.5 solar masses. These are pressure modes, but stochastically excited. They have the smallest amplitudes. What we would really, really wish for, no, this is not a young star. What we really would wish for is something like this, to find a power excess of solar-like oscillations. But this is really challenging because these low-mass stars are have the highest activity, and so they have irregular variability, like in this light curve that was obtained by Corot. And you try to find something on top of a magnitude of variability that is tiny, tiny parts per million. That's really challenging. So you have to really deal with the activity, and we are working on that. I don't say we will not be able to see it. We're just trying to find out if we can with future observations. And my PhD student is working on these theoretical predictions, describing the parameter space, answering questions like what frequencies do we actually expect exactly, that then we can say where they are in the Hertzsprung-Russell diagram. What amplitudes? The amplitudes are about the same, a few parts per million. And this is another Kippenhahn diagram for a 1 solar mass star. Again, you have the deuterium burning starting off center here. And then that's where the main sequence starts, when the hydrogen core burning starts. So this is ongoing work, but of course it tells us something about how our sun was formed and passed through its early evolution. And of course, this would be a dream goal to find the young sun. So at the end, I was asked to talk a little bit about Plato. So Plato, for those of you who don't know, just a quick crash course, is an ESA mission with expected launch in December 2026. And its core science targets solar-like stars with planet systems. So they want to basically find another solar system. So meaning solar-like oscillations in the stars and planetary systems, hopefully more than one planet around these objects. And there is complementary science, of course, with lots of topics. And for me personally, complementary science is very important because it allows me, hopefully, to observe Freeman sequence stars with Plato. So this is the Plato field of view, the Plato flower, I think it's called, where Plato has 26 cameras in total. And so they are 24 normal cameras and 2 for guiding and for the brightest stars. So the color code in the back, the blue, shows you how many cameras will observe a given part in the sky. It's in galactic longitude and galactic latitude. And so you have 24 cameras in the center, and you have smaller numbers decreasing with the blue shade. And on top of that, we plotted in black young stars from the spyglass survey with age probability more than 50%, that the probability being more than 50% that they are younger than 10 million years. And on top of that, we plotted all the young clusters also younger than, I think, 30 million years. That's what I picked because the lower mass stars are of interest. So Plato will be able to see them and at least give me, for the first time bases longer than 2 years where we can really do some interesting science with. The challenges are probably obvious. Plato has, for these young regions, a relatively large pixel size, meaning we have to deal with crowding issues. I mean, their methods have been developed. They will be applied to Plato data, but this is something we have to deal with. And of course, young stars with all their variability types, we have to find an automatic identification if there is irregular variability present, if there are combinations of variability sources. So these are the challenges that will make us busy until the launch and after that. And also something that my student sent me yesterday, or actually 2 days ago when we spoke with Nicolas, I also tried to include that. So we are now preparing for Plato and for the observations. Time is running. So he did the Hertzsprung-Russell diagram. You have luminosity, temperature here. And in gray are all the stars from the spyglass survey that you've seen before. You have some evolutionary tracks with disk-mediated accretion. That's the Sams mass of the accreting track. So that's the masses. It's more the lower masses because he's working on the solar-like oscillators. And so this is a mass of the stars in the field LOPS 2. This is the first field that Plato will observe for 2 years at least. And so the colors are mass estimates for the stars from observations. So you can see that there are a lot of stars that we will be able to observe with Plato. And we're looking forward to that. And of course, the big question is, can we observe solar-like oscillators? So what I can show you here is a light curve of a solar-like star with rotation. So we have to, of course, simulate all the activity that these young stars have. So the simplest form of activity a young star can have is rotation. So you have 2 spots modeled here that kind of interact, and on top of that, parts per million oscillations. And this is a simulation for 2 years time base with some Gaussian noise, or actually it's noiseless, if I remember correctly now. And this is the power spectrum density plot, and you would see a power axis here, and that's what we are hoping. That being said, we are now working with Nicolas to do a realistic simulation using the Plato instrument properties with Plato Sim, because that's obviously the next step. But in principle, it shows it could work. So fingers crossed that we get lucky. And another function I should mention that I am having since about 2 years. Plato also has not only has a core science and the complementary science, so core science, but they also have something called science calibration validation targets, actually thanks to Connie, these exist. And they are targets, what the name says, that should bridge the core and the complementary science. The targets come from both topics, actually. And they serve to calibrate stellar models. So we want to get precision and accuracy with Plato that we can only get if we use calibrators and validators. So there are 6 target groups. eclipsing binaries, legacy and benchmark stars, photometrically stable stars, solar-like oscillators, gamma Dorado stars, okay, the gamma has gone, no transiting exoplanets. So from these 6 groups, they will serve to calibrate the stellar models. And photometrically stable stars, for example, are needed to see if the observations have an instrumental problem, if there is a jump or so, just as a background. And so I'm leading this team of several people. Most of them are listed down here. The group is increasing. Actually, every few months we get a new member. And so last year we had to deliver the first catalog of these science calibration and validation targets, SCV PIC. It's 38,402 targets in this first field, and we are now about to deliver an update with the beginning of June of that, and this will be then implemented into the Plato input catalog, the PIC. So this is very important work, and we hope we can contribute to the success of Plato. So I'm coming to the end. Just summarizing a bit. So I think it is important that we improve our concept of star formation when we do asteroseismology because it has an impact on our interpretation. It might have an impact beyond the TAMS. This is also something. It gets, of course, more challenging because you have other uncertainties in stellar models on the main sequence and beyond that can contribute. So, but I'm sure that there is also an impact beyond the main sequence. At the moment, our models do not contain magnetic fields and rotation, but we have already started first steps in improving that. On the other hand, we can turn things around. There are stars like FU Ori stars that have these accretion episodes, and these are confirmed that these luminosity excursions really exist. And at the moment, we also have some work. We try to predict the accretion episodes happening. So we could probably say in 150, 200 years, the star will undergo an accretion episode. This is something that is now a little project with us. And of course, we need to increase the numbers per group. Like I said, the gamma Dor stars is underrepresented, so we need more of those. This allows group studies, finding empirical relations and other things, and I think Plato will be a game changer. And with this, I thank you for your attention. If you have questions.
That was long. Very nice. Thanks, Konstanze, for a very nice overview. We have about 10 minutes for a discussion that we can then continue during lunch in our kitchen. Who wants to ask a question or make a comment?
I mainly work, thanks for your great talk. I mainly work on like stellar evolution models that go post-main sequence and post-TAMS. But you showed that the model actually, it doesn't matter what pre-main sequence we do, they all end up at the same spot. So how much does it matter for my stellar evolution models what pre-main sequence I take? Because I assume that whatever you do takes a lot more time than what is currently implemented in, for example, MESA.
That's a very good question, a very excellent question, and I'm sorry I will not be able to give you a full answer, because at the moment we know it has a difference up until the TAMS. We did some work that goes until the terminal age main sequence, but we were not allowed to publish it because the referee was seeing this too critical. The referee said there are other effects, and he or she was right. There are other effects that might play a role, so it's probably not so easy. But we see from what I have not published, but you have only to trust me here. So we see the effect decreasing while the hydrogen core burning is going on. When the hydrogen core burning is about to stop, or when the core content is dropping to the last percents, we see the differences coming back again. So this is something I would like to answer. So this is why I say this is your question is really excellent, and there's way more work needed Also may work on input physics for models in all stages. But this is something, yeah, I would also like to know. So I share your question, actually.
Thank you for your honest answer.
More questions?
Hey, Konstanze. Thanks a lot for the nice talk. I was curious, actually, what are the observational challenges for detecting these cool pre-main sequence? Because you do predict this zone, right, where these guys are expected. So is it just, so they should exist, but why haven't they not been discovered yet?
Okay.
You had it in the previous slide. Yeah,
Yeah, I can be a bit more specific on that. So we are facing, for pre-main sequence asteroseismology in general, we're facing the problem that the space missions in the past, and okay, let's exclude TESS for the moment, but for example, Kepler pointed away from young regions on purpose. And so there is not a single pre-main sequence star in Kepler. It can't be because it's outside of the galactic plane. I was a student when Kepler was being designed and built, and I'm still, it hurts me a lot that we did not, that it was pointed away from this. So K2 made a little bit of a difference. There are some observations in Upper Scorpius, but the time bases are 80 days, which is not that long. Then TESS came. TESS, you know, a sector is 27 days. There are some stars that have more than one sector. Sometimes the observations are repeated after 2 years. But the time base maximum that we are currently having is about 100 days. So 100 days of a low mass star that is highly active and has oscillations is not sufficient to detect. Because this is why I put this up. If you have a light curve, if the magnitude of the star changes by a magnitude, a full magnitude due to the circumstellar disk, and that's what these stars have, and you have on top of that these tiny oscillations, I have to be honest, with 100 days it's impossible. We have simulations that can show that. You can be a bit more optimistic and say, okay, if I have a rotator, so some of these T-Tauri stars only have spots, and what you see in a light curve is rotation, but you still have 100 days, and parts per million amplitude we will not be able to detect. So we are lacking the observational material. This is why I think Plato will be a game changer. Earlier missions had shorter observations, so like 30, 40 days, Most and Corot delivered those. So the maximum we're having, that's basically the honest answer, is if we would have 4 years of Kepler, we would have found this. I'm pretty sure.
We still have some time.
Thanks, Konstanze. I have actually a question for slide 24, because when I looked at this the other day, I didn't have this question, but now it it just came. So you have a lot of stars missing in a temperature range here. That's just a gap. What's happening here?
You mean this one?
Yeah.
I don't know, like, I've seen this plot 2 days ago, like you.
Yeah, okay.
So
maybe
the way we do it, this is the spyglass survey. I actually remember now, because it's combined with Gaia information. And it might be that there is no Gaia information, no mass estimate for these stars. So only the ones are highlighted that have a mass estimate. And so I guess there are way more, but they don't have a mass estimate yet.
Yeah, okay, that makes sense. Because I was thinking maybe
Yeah,
physically they will be there in the field.
Yeah, that's what he said. But this is a spyglass survey. It has a lot of huge table, and you can, take the youngest ones. We can relax. You could actually relax the criterion because a low mass star takes longer until it starts to burn hydrogen. So you can also have it with 30 million years or 50 million years. So you could probably relax the criterion that was used to plot this. But I wanted to share the recent results with everyone, so this is
Thank
fine.
you, sorry.
Thank you. Katrin? Okay. Okay. too many. We can continue. I'm around the whole day. Just grab me.
Hi, Konstanze. Thank you for a wonderful talk. I liked your suggestion of a three-dimensional HR diagram to make these pre-main sequence stars stand out. So what parameter that you could observationally determine or that could be theoretical would you put on the third axis?
Ooh, that's a good question. So I think the easiest, I mean, I'm thinking of a diagram that is easy to grasp for students and for the public, for everyone. So not a scientific graph. It's something like this asteroseismic Hertzsprung-Russell diagram. You can tell people what you see. So then the obvious thing would be something like age. Yeah? That was probably the obvious choice, that you would have age on the third axis. You can maybe find another parameter. I have a certain opinion on stellar ages, but I will probably not revolutionize the whole field of stellar astrophysics. I would like to really have 0 age on the main sequence and count backwards and forwards from age equals 0 on the main sequence, because this is a well-defined point.
Yeah.
But nobody will do that. We all live in this, we are born and we evolve and we're children and adults and we die. And that's what we imprint on the stars. And it's a natural thing. But for me, age would be really from age 0 on the main sequence and then going backwards and forwards. That would make more sense to me. But
okay, thank you. Yeah, because you could express age in, in years, but also maybe in some other parameter that could measure.
Exactly, something that reflects age.
Yeah, okay, thank you very much.
Yeah, maybe the last question.
That was a very nice talk. Even as a non-astroseismologist, I think I know what you're doing. But I was wondering, how sensitive are your results on the underlying physics, for example, like the treatment of mixing length theory, opacities, and so on?
Absolutely, a very good question. So for those of you here who know, we are using MESA. We are coupling this accretion physics to MESA. In MESA, you choose several things. Opacities, of course, it depends on everything. On opacities, it depends on the treatment of convection. I think we have a mixing length theory from Cox and Julie, for example, for mixing length for convection. Of course, if you change how you describe convection, there will be changes, and this would have to be investigated. My former PhD student made a lot of tests with atmospheres and opacities. It's all published. There are tiny differences. They don't impact so much. On metallicity, so we did a lot of different tests. Overshooting, mixing regions. There is a tiny influence on the models, of course, when you have to do a wise choice, but it cannot explain the differences we see.
Thank you.
All right, we are at the hour, so I suggest we stop here and thank Konstanze again.
Thank you.
Thank you all for coming, and just a reminder, or maybe new information for some of you, next week we are not going to have a seminar because nobody wanted the slot, but I will see you here in 2 weeks from now. Thank you, guys.